Hello and welcome to the MOOC on optical communications. We have seen optical transmitters, we have seen optical receivers. That was a big picture context to see where optical communication system fits in. Of course, optical communication would not exist without the optical fiber itself and of course a laser source or a light source in order to send light, but that is a different part of the story. We will come back to that one later. So, the principal reason why we do have optical fiber communications is because we have a low loss large bandwidth optical fiber. That is, the optical fiber loss is so low that one can go considerable distance, typically about 80 to 100 kilometer in the long haul links without putting up an amplifier. So, of course, at that stage the signal quality would have degraded, but this is a very large distance. If this large distance can be compared to much shorter distances that you would have had to use if you were to use a copper cable in order to connect the whole wide world. So, optical fibers have low loss, which means long distance propagation is possible. Optical fibers also support a large bandwidth. The operating frequency of the laser itself is in terahertz. So, even if you were to able to just tap 10% of that terahertz signal, then you are already looking at a very large bandwidth. Moreover, by multiplexing the channels, you can actually and implementing spectrally efficient modulation techniques such as QPSK or higher order QPSK, QAM, as we discussed in the transmitter side, it is possible for us to improve the data rate as much as possible. Now, what we will do is we will begin with consideration of optical fibers. I will give you a very brief overview of the optical fiber history and then quickly jump into what is called as geometrical optics analysis of optical fibers. This geometrical optics is kind of very simple analysis in the sense that it is actually a simplistic analysis. It works under certain conditions, but in general if you want to understand more about optical fibers, the propagating modes and how light actually propagates inside the optical fiber, then you have to study it from the electromagnetic theory perspective. However, we will, of course, we have already looked at electromagnetic review and I am assuming that you have done a course on electromagnetics, but geometrical optics provides a little bit of intuition which we will be gaining if we study with the geometrical optics approach, and moreover it is kind of simple. We will understand a little bit about optical fibers and how the mode propagates in a simplistic way by looking at geometrical optics. Later, of course, we will use electromagnetics to actually know how the light gets distributed inside the optical fiber. Okay. So, let me begin by highlighting the kind of short history around here. Optical fibers, the concept of an optical fiber was not new, it was there from the earlier times when light itself was used as communication tool. However, the realization that silica made or silica dielectric rods, which were what they were called earlier, can lead to optical fiber production and can lead to low loss optical fibers, was actually made by a couple of people. One is Charles Cow, he was working in the Bell Labs at that time when he made this kind of prediction, or rather a nice case for optical fibers, I should say, not prediction. It was a nice case of optical fibers. Optical fiber type guide waveguides were already studied, but the importance of them for communication was realized by Cow, wherein he published a paper in the year around 1966, which was a very famous paper by these two authors, Cow and Hocum. So, these two guys published a paper where they analyzed the existing silica dielectric rods, what are the modes of propagation, and they also predicted that if one could find a fabrication method which can cut down the losses, then this can be used for optical communications. Okay. So, it was kind of a realization that even though sometimes it is very obvious that if you simply cut down the losses in an optical waveguide, you can use it for communication, it was not appreciated at that time. When Cow and Hocum made this analysis, the people around them got so excited, they started really working towards achieving the loss. So, at that time if you wanted to replace the existing copper cable network by an optical fiber, the target figure for the loss was 20 dB per kilometer, because this is the typical loss that microwave links which used links which used copper cables were giving. So, if you wanted to target, if you wanted to say that, hey, no, you see, you throw out all the copper cables in the world and replace them with these very thin silica rods, then it was necessary to convince the industry that this target loss of 20 dB per kilometer can be met, and this was made possible in the year 1970 by a process known as chemical vapor deposition, which brought down the losses to less than 20 dB per kilometer. Once it was brought down to that level, work intensified so much that in the early 70s, in the early to mid 70s, the losses were already down to 5 dB per kilometer, which is way below what the copper cable can do, and it was realized that the main contamination to this was the water contamination. So, it was people understood it very well, and therefore, they also came up with methods to remove these contaminations, and eventually brought down by the late 70s, just about start of the 80s, the losses were brought down to 0.2 dB per kilometer. Now, that is an extremely small value compared to 20 dB per kilometer, and remember, this is the dB scale. So, if you go one order magnitude down, you are reducing by 10 times, like you are going by that one. So, you go that way, so you are quickly building up to the dB scale. You can appreciate very well that from 20 dB per kilometer losses, we have come down to the existing optical fiber losses around 0.2 dB per kilometer, and the theoretical predicted loss for the silica fibers were around 0.15 dB per kilometer. This one can obtain after looking at various type of scatterings, loss, and material composition of the silica fibers. So, this was the ultimate limit kind of a thing, and it looks like we have even recently reached almost to the theoretical limit, not even 0.2, the losses have been cut down even further. So, the loss property of an optical fiber, which is very low for fibers, was made possible by tremendous efforts of so many researchers, where they started off from 20 dB per kilometer. This was a magic figure to achieve. From there, the losses were steadily brought down to the existing levels of 0.2 dB per kilometer. Of course, I have told you only one part of the loss story, because loss is also wavelength dependent. So, if you go to different wavelengths operating region, then the loss also changes with that, with typically the lower wavelength regions having higher losses and the higher wavelength or the longer wavelengths having lower losses. Okay. So, based on that, optical communications started operating in different kind of windows, as we call them. We will talk about that in the next few minutes. Now, what different type of fibers are available in the market today? Fibers not only characterized by their loss, they are also characterized by the area of the core, the total area of the fiber itself, and whether they are single mode fibers or multi-mode fibers, and whether they can cope with dispersion or they cannot cope with dispersion. Can they maintain polarization? Are they insensitive to bends? Can the nonlinearity in the fiber, a topic which we haven't touched, a nonlinearity in the fiber be increased? Is it possible to come up with very interesting speciality type of fibers which will do even things which are not a typical fiber can do, and can it also be possible to reduce the nonlinearities in the fiber? Is it possible to excite multiple modes in the optical fiber? If we can do that, what type of a fiber should we have? So, all these parameters determine the type of fibers that are available in the market. The primary type of fibers that you can find in the market are the single mode fiber and the multi-mode fiber, and all these other fibers can come in the versions of single mode and multi-mode fibers. What we mean by single mode fiber is that for a given frequency of operation, there is only one mode. Electric field pattern and magnetic field pattern together is called as a mode. So, there is only one mode which will propagate inside the fiber. Okay. So, when it comes to multi-mode fiber, as you could have easily guessed, multi-mode fibers will have multiple modes, it can support multiple modes, although it seems that this idea of multi-mode fibers is very interesting. Rather than restricting ourselves to only one mode carrying the information signal, why not use a multi-mode fiber and have many modes carries information signal. It turns out that in the 70s, 80s, 70s it was quite popular, 80s it was already beginning to go down, 90s it was not, 2000s it was not. The reason for why MMF was not popular for long haul communications was because it introduces what is called as intermodal dispersion. Okay. These signals which are carrying with each other, they start to talk to each other, and then there will be distortions and the total error rate of the system increases, and therefore, this was not a preferred choice. Of course, MMF can be easily excited by coupling it to a cheap LED, and this MMF operating in the 850 nanometer was quite popular for short distance communication such as Ethernet. Today multimode fibers have made comeback in some specialized areas where people have learnt how to uncouple these couplings that exist between the modes inside a multimode fiber. So, this uncoupling is done not in the optical domain, but that is done in the digital signal processing domain. So, having said that, we will concentrate for the theoretical purposes or for the course purposes to understand the properties mainly of the single mode fiber. We will go to multimode fiber as and when that is required. I said that dispersion is a major factor in optical communications. In fact, we will later see that dispersion limits the bandwidth or the the bit rate of the system. In order to cope with dispersion, there are a lot of ideas people have come up with over last 30-40 years. One is the so called dispersion shifted fiber, which has a zero dispersion wavelength located in the C band. I will tell you what these bands are later. So, this is the one where we are operating at 1550 nanometer, and the dispersion shifted fiber has a zero, that is zero dispersion at 1550 nanometer. You also have a dispersion compensating fiber. Suppose you have a single mode fiber which is characterized by positive dispersion, whereas DCFs are characterized by negative dispersion. So, if you put one after the other, you can see that dispersion can be compensated if you choose the appropriate lengths and powers. There is also what is called as dispersion flattened fiber. Here the dispersion curve is almost constant with respect to wavelength. So, this is used in other specialized applications where we know the amount of dispersion, or rather we want to minimize amount of dispersion that over a wide band of information bearing signals are subjected to. So, it is like a kind of a band over which the dispersion remains constant. Therefore, all the signals within this band are unaffected by dispersion, or rather they are affected by dispersion with the same value. It was also realized that having DSF would increase nonlinearity, because nonlinearity and dispersion are like yin and yang. One goes up, the other goes down, the other goes up, one goes up. So, if dispersion goes to 0, that is where the area where nonlinearities can really take off and create a lot of troubles. Therefore, it was realized that, well, we do not want to make the dispersion 0, let us just raise the dispersion a little bit so that the overall efficiency of nonlinear generation comes down. Okay. So, this type of fibers are called as non-zero dispersion shifted fibers, and these non-zero dispersion fibers have a small amount of residual dispersion which will then allow it to counteract the nonlinearities. These are some of the specialty fibers that you can get in the market. BIF is called as a bend insensitive fiber, and this is majorly applied for the fiber to home networks, wherein it is the fiber has to go from home, from say your room to your parents' room for example. There as the cable goes, there will be bending around the edges, because no one likes to have a fiber hanging out like this, right. So, you want all the fiber lines, just like the power cables are buried inside your house, you want along that same lines your fiber also to be buried or guided by the walls rather than by just hanging around, which inevitably leads to bend in the fiber, and bends in the fiber reduces bend in the fiber actually increases loss a lot of, it increases loss, it will also alter the dispersion. So, in order to cope with this problem, bend insensitive fiber or bend managed fiber are used, which will have little bit of less sensitivity compared to typical single mode fiber for bending. You have a polarization maintaining fiber which will maintain the X and Y polarizations inside the fiber. Suppose you launch a signal at X polarization, then at the end of the fiber you are guaranteed to have the same polarization by the polarization mode dispersion. If you want to perform some nonlinear optics, nonlinearity is not always bad, it is good in many cases of optical signal processing. So, if you want to use your fibers for that, you want your fibers to have a high nonlinear coefficient, and those fibers are called as HNLF, that is highly nonlinear fibers. And this last fiber which I mentioned can do very interesting things. This is called as photonic crystal fibers. So, these are kind of fibers plus filters integrated together. I mean, this is a very simplistic definition that I am giving, but this photonic crystal fibers can do lot more interesting things than what I have just told you now. Finally, large mode area fibers are available which have a larger mode area, and nonlinearity being inversely proportional to the area. If you increase area, nonlinearity comes down. I also forgot to put one more fiber here, This is called as a few mode fiber. A few mode fiber has typically like only 1 to say 6 or 1 to 7 modes. Sometimes there is a specialization of the few mode fiber called as dual mode fiber or 2 mode fiber, in which there are only 2 modes. Okay. So, these few mode fibers have much less modes, they can support much less number of modes compared to the multi-mode fibers, whereas multi-mode fibers can easily support up to 15 to 20 modes. Few mode fibers can support say about 6 or about 5, and that already is very large for this. Finally, you have what are called as multi-core fibers. Rather than having a single fiber with a single core, you now get multi-core fibers. The idea here is like you have taken a multi-core fiber, each of these cores can then carry information signal. Okay. So, it is like you are putting some parallelism, you are having an antenna and then you are beaming it into 4 different areas. It is kind of a broadcasting thing that is being looked at. So, these are all the different type of fibers, and these fibers all are characterized by different geometries, they are characterized by different core areas, they are characterized by different cladding diameters, cladding. They are also characterized by the refractive index profile. So, some fibers have a trench in order to make them be less bend sensitive than others, and some have no trench, some have a step index fiber, some have a graded index fiber, some have a very interesting fiber profiles in order to achieve this DSF, DCF, DFF properties. Okay. So, we will see some of those later when we discuss the summary of different type of fibers after we have learnt the modes. Okay. Now, one last point about the operating wavelengths in optical communications. The early optical communications was made with the help of LEDs and multi-mode fibers. It was easy to couple up LED and multi-mode fibers, for which the core diameter, or I think core radius or core diameter, I am not very sure which one it is, was 50 micron, became 62.5 micron, and then it was pushed back to 50 micron in order to make it compatible with the LED. So, this 850 nanometer was the first window of operation where much of the optical communication was taking place. This of course was in the late 60s or early 70s. Then people figured out that if you go to a higher wavelength 1310, loss goes down. So, the next window of operation was 1310 nanometer. It also had a bonus because the zero dispersion wavelength of the fiber was the zero dispersion of the fiber, which is silica material dependent, was at 1310 nanometer. So, it was made up of silica, and this silica had a zero material dispersion at this 1310 nanometer. So, it was quite interesting to work with both low loss as well as zero dispersion. However, people realized that 1550 nanometer gives you even less loss than 1310 nanometer, and loss is sometimes very important because you do not want to put too many amplifiers in between. You are willing to take a little bit of hit on the dispersion and reduce your bit rate, but you do not want to increase your infrastructure cost by putting up your amplifiers at a smaller repeater spacing. So, loss was very attractive. So, 1550 nanometer has become the operating wavelength for optical communication since the 1980s. Okay. So, this band is conventionally known as the conventional band or the C band. There is also a long band at 1600 nanometer, wherein we are looking at how to use different technologies in order to communicate at 1600 nanometer. There is not much of a success yet, but C plus L band is expected to satisfy the customer needs for at least next 10 to 15 years. So, this was just a brief about optical fiber history, started as to what was the magic figure of 20 dB per kilometer, and then what was a theoretical limit, and then to show that we have in fact achieved theoretical limit. So, this in terms of the loss has been reduced considerably. Then for different applications, where you want to highlight some factors, you do not want to highlight certain factors, you can find many types of optical fibers. So, you can find many type of optical fibers. Finally, I also gave you a brief overview of the windows of operation, which means that we are selecting different operating wavelengths based on certain parameters such as loss and dispersion. A typical single mode fiber will have a certain core radius. Okay, this is around 4 to 5 micron core radius, and the diameter is about 8 to 10 microns, and then it is also doped with certain materials. The basic material is silica, but it is doped with certain materials in order to raise its refractive index to N1. So, let us call this as refractive index N1 and let us call the core radius as A. So, this A is typically 4 to 5 micron, making the diameter as say 8 to 10 microns. The refractive index N1 is in the order of 1.44 something. Okay. Now, surrounding this is a cladding which is actually standardized at 125 micron. So, this radius is standardized at 125 micron, if you can call this radius as say B. So, B is typically 125 micron and the region outside the core. So, this of course is the core and this is the cladding. Okay. So, this is the core and this is the cladding. Surrounding the core is the cladding and the cladding has a refractive index of N2 which is less than N1. I will tell you why N2 has to be less than N1 in a moment, but this is how it is done. But you might ask whether N2 is less than N1 is a very broad statement. Is there any particular difference between the two? It turns out that N2 is not like say 10 times lower than N1. Okay. It is not like this. N2 minus N1 is typically about 0.1 to 0.4%. I think it is about 0.4% is the refractive index difference for standard single mode fibers. Okay. So, such small refractive index difference is required in order to make the fiber single moded for the given core radius and the refractive index that is surrounding them. Surrounding all this would be a jacket which is typically at around 250 micron. So, you can clearly see that the way I have drawn this one is not really capturing the scales properly. So, the jacket is typically around 250 micron. This is further protected by a coating in order to make the mechanical properties of the fiber little better, and then these are put in tubes and then these tubes are loosely bounded and then they are put into rods and these rods are located along the ducts. So, this is how the fibers are taken up from and they are laid, but the important point is that if you were to look at the refractive index distribution as a function of the different regions, you will see that right at the core, over the core region, you are going to see refractive index of N1, assuming that this is what is called as the step index fiber. Then once you reach the cladding, the refractive index becomes N2, which as I said will be less than N1, and finally when you reach to the coating outside or the jacket outside, the refractive index goes to N3. So, this is N3. So, this of course has to be N2, and as I said N2 must be small compared to N1. Okay. So, this is how the refractive index of the fiber looks like. So, if you call this as the radial axis R, so the refractive index is N1 until R equal to A, it is equal to N2 until R is equal to B. Okay. Since this jacket is really far away from the region and it does not really contribute much to the propagation properties, we kind of analyze an optical fiber as though it consisted only of a core and a cladding. So, this is kind of the relative scale accuracy that you are going to see. So, you can see that B is roughly 125 micron and A is around 5 micron, let us say, just to round off the numbers. So, clearly B is about 25 times larger than A. So, the region of the cladding is much larger than the core region. Okay. So, much of the properties are of the optical fiber modes are dependent on N1, N2, A and B. Okay. We will see later that one, and since B is sufficiently large, it does not really contribute much to the propagation. So, it is only N1, N2 and A that are primarily very important for the calculation of the optical modes. Now, what I will do is in the next 5 minutes give you very simplistic view of how a mode is propagated inside an optical fiber. Let us assume that this is the optical fiber, this has a nice cylindrical cross section and there is an axis of the cylinder along like this. Okay. So, this is the axis of the cylinder. Now, what we do is we shine light at a certain incidence angle. Remember, incidence angles are to be measured with respect to the normal. In this particular case, the normal happens to be at along the axis of the cylinder, therefore, this is theta I. So, this is the light that is coming in. Outside here we will assume that this is air, therefore, the refractive index here is n equal to 1. Now, as this ray of light comes and hits this particular axis, right, this particular interface. So, you can imagine that this is the optical fiber that I have, okay, and then I have a normal to the axis. So, let us just locate it like this. So, this is your normal to the axis, and then we come in with light. So, maybe we come in with light like this. Okay. So, now you can see that my finger is actually making an angle here, and the angle that it is making with respect to the normal is theta I. So, what should happen to the incident ray of light here? Well, you see there is an interface here. This interface is the core area, and the core which is separating the air and the core has a refractive index of n1. So, Snell's law applies here, and what you get is a refracted ray. So, the ray basically gets refracted, goes into the core medium and then hits the cladding interface at this point. This ray refracts and then hits this cladding interface. So, maybe we will call this angle of angle at which this second ray, refracted ray, hits as phi, and this angle is theta 2 maybe, and this is phi. Now, this is one more interface. Here you have n2 less than n1, here you have refractive index of n1. If n2 was greater than n1, what would have happened? It would have simply refracted again, right. So, the ray would have refracted again had n2 be greater than n1. So, there is nothing happening out there. There will have been, of course, some partial reflection back into this region at the same angle phi, but the power would not have been completely reflected back. So, the transmitted wave or the refracted ray would have carried significant amount of power. However, now suppose when you have n2 is less than n1, there will be no transmission into the cladding, but entire transmission will be along into the first region itself, provided this angle phi is greater than what is called as the critical angle of the interface. The critical angle of the interface is a function of n1 and n2, right, as well as the angle of incidence phi is actually the function of n1 and n2, and for a given angle of incidence phi, if it is greater than phi c, total internal reflection takes place, which will cause all of the power to be reflected back. So, this is how once it is reflected back, assuming that this angle is again larger. So, if this is larger than phi c, this would also be larger than phi c, ray will be reflected again and again there will be reflection, and by these successive reflections is how the light propagates inside the optical fiber. So, we will stop here and continue in the next module. Thank you.